Okay. So let us take this. What is that? Let us say we have data coming from somewhere. Okay. Say this is the data coming. Fine. Now this data is like x1 y1 x2 y2, these tuples, so on up to xn yn. Okay, now how is this data generator generating this data? Let us say this data x1 y1 x2 y2. Okay, let us say this data generator is doing something like there is a domain x and there is a domain y. These x1 x2 x3 and so on up to this are points in this. And then these y1 y2 y3 are points in this. Now this data generator actually has a function that maps from this to this. F is a function from x to y. Now whatever that function is, this data generator is using that function f, that function is f, to generate these data points. Okay. Okay, fine. Now, usually, what is this data generator in our real life? It could be anything. It could be the experiment that we are working with. An example could be Boyle's law. If you are testing Boyle's law, what would you do at constant temperature? We would change pressure and record volume. So then in such a situation we get some data and we plot it, and the points would be this. Okay, something like this. Pressure, volume. So here our data now this is our data generator. This, we start from this saying that this is our data generator. Okay, so at one side there is pressure, the other side there is volume. We want to find what this function is.
So we need to find the function.
So we want to find what this function is. What the function this data generator is using so as to find the good, so as to fit this data. So people call this curve fitting and all that. People call this curve fitting. In statistics. But for all this we need something. We need some criterion. Some criterion to be discussed. The criterion is about the error after the curve is fit. Why is this important? Because this error would signify how good the curve is on the experimental data. Okay, that is data obtained from nature. Right?
Yeah.
So we have to define some error function. Right? So there are two kinds of error functions. One is generalization error. Okay, function, and the other is it is called empirical loss function. This might also be called generalization loss function. Okay, now let us see what is the difference between these two. Generalization loss I will not discuss now. I will discuss in a later video when it is required. I will discuss the empirical loss function. So for empirical loss function, we first need to know an expression. Okay, so this is E empirical loss function. This is sigma L of yi comma xi or xi comma yi for I is equal to number of samples n, sample size. Okay, now what is this L?
Okay.
So we have L of xi comma yi. This has to be defined.
Okay.
Now let us say we denote the relationship of xi and yi by a hypothetical function say small f. Okay, now yi is equal to small f of xi, because we had this diagram
Okay, right.
x and y, and then we said this related by some f. Okay, so now we define this loss function. This is loss function for a single sample. This as L of xi yi is equal to f of xi minus yi or yi minus xi. Let us take yi minus xi, f of xi whole to the power p.
Okay.
Fine. This is in general for any p. We call this the Minkowski loss. Okay, this is called the Minkowski loss. This is loss for a single sample. Fine. Now for the special case of p is equal to 2, we call it squared loss.
Sure.
Okay, this is called squared loss. So let us for now only discuss squared loss, and then also see other kinds of losses as we progress. Okay, so L of xy is defined as y minus f of x whole squared for squared loss. Now sigma I is equal to 1 to n, L of xi yi is sigma I is equal to 1 to n yi minus f of xi squared. The other thing, here we divide it by the number of samples whenever we want, so as that the numerical explosions do not occur. Do you see that?
Just kind of
Normalization kind of thing. So this is the normalization, so that numerical explosions do not take place.
okay.
Fine. So this is our what is this? Empirical loss function. Okay. So all that we want is, for any f that we want to realize, we should make sure that the error is minimum. Isn't it? So if you want to make sure that the error is minimum, that implies that this function should take minimum value, right? Or this not this function, this expression should take minimum value. This is not empirical loss function, this is simply empirical loss, because yi and xi are put and you finally get a constant. Okay.
Right.
Here I call it an empirical loss function. Empirical loss function because we haven't yet. Okay, even here it is empirical loss and generalization loss. This is your loss function for a single point. Loss function for a single point. Okay. So fine. So let us see this. Now let us say this. Now we have we have something called the hypothesis space. Now this f that we are calling it here, say this is your x and this is your y, right? And there is this f here. Fine. Now there is a space called hypothesis space, and this f is called hypothesis.
Okay.
Hypothesis. Now there is a space called hypothesis space where this f lies. Let that space be here. I will call this the hypothesis space. Now in this hypothesis space there are all possible f's. Do you see that?
Yeah.
Now I want to pick some f from this space so that it minimizes my loss, the squared loss. I want to pick some f from this space so that whatever I get minimizes squared loss. But then in this hypothesis space, let us make a constraint. I will say I just want to pick from this area. Okay, and this area is area belonging to linear functions. Okay, I know I am restricting a lot, but that is what we want to first study.
Yeah. Okay.
Linear functions. So we want to find a linear function f so that this happens. Okay. Now let us get to some real framework. Until now this x and y were abstract space, some abstract quantities, weren't they?
Okay.
This was an abstract domain and this was an abstract range. An abstract domain and this was an abstract range. I didn't tell you what these elements in this domain were. So now let us specify till now. This was the story till now. Now let us specify something from here. So that something is, let each element x belonging to x be in a space Rd, where D is the dimension of the space.
Okay.
D is the dimension of the space. And then let y belong to let a small an element y belonging to capital Y. Let y belong to just the scalar space. We could also take it. You could also take it to be complex, but let us take it real scalar. So it is like a vector mapping to a scalar. So we have constrained ourselves for this as a vector mapping to a scalar. So that was x to y f was x to y, and then this was a subset of Rd, and this was a subset of R. Okay, writing it clearly, x is a subset of Rd, subset, not belong, because x is a set, no, and y is a subset of R. Fine. This is what we are doing, right?
Okay.
Now, how do linear functions be in this space? So let us call linear functions as f of x is equal to some w0 plus w1 x1 plus w2 x2 and so on up to w dxd.
Okay.
Because it is a d-dimensional space. That okay. These are actually affine functions because there is a constant, but let us for the present call it linear functions. I'll justify why we are calling them linear functions. Okay. Now, where x is equal to x1, x2, so on up to xd, and x belongs to this, which is a subset of Rd. Fine. Okay, this is clear. Now, let me try to see this in a different way. So, if I want to see it in a different way, what I would do is I would do this. F of x is equal to, from our very good dot product notation or inner product notation, I can write xd, but I have to put a 1 here.
Put a 1, yeah.
Okay. Now tell me, to which space do these two belong to? This and this vector.
Rd plus 1.
Yes, exactly. So say w is equal to w0, w1, so on up to wd, and similarly x is, now let us say this was x tilde, let us from now call this as x, the new one. So this was x tilde, let us call this as x. So this is x is equal to 1, x1, x2, so on up to xd. Fine. And this w and x belong to Rd plus 1 space. Now you see, we nicely have f of x as w transpose x.
Yeah.
See that additional constant is absorbed inside. The additional constant w0 is absorbed inside. Do you see that? So now you can call this a linear function.
Yeah.
So we can now call it a linear function. That's why we call it a linear function here, though it is affine. Though this was affine, we called it linear because we knew that we would do this. Though this is linear, though this is affine, we called it linear because we knew we'd do that. What are these coordinates called? These are called homogeneous coordinates. Okay. This kind of representation by increasing the dimension of space as required is justified by use of these extended coordinate system called homogeneous coordinate system. Okay.
Okay.
This homogeneous coordinate system is used a lot in projective geometry.
Sure. This thing.
Yeah, in computer vision.
Okay.
Okay, that is fine. So now we want to find what this function f of x is equal to w transpose x. So what do we want to find here? We want to find these constants w0, w1, w2, so on up to wd. Fine. We want to find these constants given that we have the data from the data generator. What is that data? x1, y1, x2, y2, so on up to xn, yn. Okay, fine.
Okay.
Now let us try so since we have each of these, we have f of xi is w transpose xi. That implies we have f of x1 as w transpose x1, f of x2 as w transpose x2, f of x3 as w transpose x3, and so on. We have this f of xn as w transpose xn or xd. Fine. xd as w transpose xd. Fine. So, but we have this error also in every of this sample. What is that? L of x1 comma y1 is y1 minus w transpose x1 whole squared. Similarly, L of x2 comma y2 is y2 minus w transpose x2 whole squared, so on up to L of xd comma yd, which is yd minus w transpose xd whole squared. Fine. Now we have our loss error. What was that loss? Empirical loss. Empirical loss as L is equal to, what is that? 1 by n sigma I is equal to 1 to n yi minus f of xi whole squared. Fine. So let us substitute that here for our special case of linear squared loss. Linear functions are to be chosen from the hypothesis space This is the constraint that we put in. Do you understand that?
Yeah.
This was that constraint.
Linear.
We only want linear functions to be picked up. Okay. So, what do we have? So we have this. So that is 1 by n sigma I is equal to 1 to n. Yi is the same yi that we had minus w transpose xi.
Yeah.
Fine. Now we want to do more about this. Before going anywhere else, let us try to do something else. Now we have y1 is equal to w transpose x1, right? There is a small inconsistency in notation, that is these coordinates x1 x2 and all, no, these are not x1 x2. Let us make a small change. These are, say, x11 x12 xd1,
And x1 is the entire.
entire, yeah, x1 would be entire of that. So
Otherwise,
yeah, so okay, this is not I, this is not 1. Let us make it x1i, say this is xi, x2i, so on up to xdi.
Yeah.
Fine. Or wait, so as to be consistent in the future, let us make it xi1, xi2, so on up to xid. Okay, fine. So the same thing here. xi1, xi2, xid, for each of these to be xi's. Fine. Okay, this is clear.
And what about that? Yes. Fine.
id. Okay. Yeah. So now this is y1 is equal to x1. Then I have y2 is equal to w transpose x2. Then I have so on, yd is equal to w transpose xd. Okay, this is fine. Now we will write this as a vectorial form. y1, y2, so on up to yd is equal to x1 transpose here, x2 transpose here, so on up to xd transpose times w0, w1, wd. Can I do this? Because
But second.
w transpose x1 is equal to x1 transpose w, because this is a scalar.
Yeah. Okay,
So
listen. Initially हम लोग we took x1 as w transpose x1 as a right.
we took y1 as w transpose x1.
Last slide में देख, last go to the previous slide. No. और पीछे और पीछे. Just check. ये अरे इधर fx1 as
w transpose xi.
and again you are taking y1 as
See, this is what we want, isn't it? This y1, this is what we want to find an optimal w, so that this is satisfied, so that these equations, do you get that? We want an optimal w so that these are satisfied. We don't know what the w is yet. Okay.
Yeah.
Now this discussion was, I found a w. This discussion that I told here was, suppose that I found a w and I plug that w here, because we may not always find a possible w here. This is hypothetical. That's why we call this as a hypothesis. Okay. Here this w is, that's why called the hypothesis. This is hypothetical. But then let us assume we somehow found some w. and then we put that W here and we find this loss. Okay, so that is what this is. We want this yi is equal to W transpose xi. We ideally want this. We ideally fine. So x1 transpose so this I would write it this way because of this property. Fine. Now let me say this matrix x1 transpose, x2 transpose, so on up to xd transpose is the matrix capital X, which is the data matrix. Fine. Now, one more thing. It may not be D here. It may be N also. This is N actually. Number of samples. Number of samples of data that we have. Fine. So, it depends on the number of samples of data. So, that would be Xn here. So, what is the size of this matrix? R n cross D. D plus 1. Each of X is D plus 1 and that is transpose, so D plus 1. R of n cross D plus 1. Fine. Now, I can now if I make this matrix y, y1, y2, yn, y1, y2, so on up to yn as some y. Okay. Then this y belongs to R D plus 1. Fine. And x already small xi already belong to R D plus 1. So, now we can write this entire expression y1, y2, so on up to yn times ym is equal to some x1 transpose, x2 transpose, so on up to xn transpose times w0, w1 to wd as, and if I denote this w0 to wd as this W matrix, where W also belong to RD plus 1, then I can always write this as y is equal to xw. Fine. So we have this, or xw is equal to y. Fine. So the thing here is we want to find optimal W such that the above is satisfied. Fine. But then this might always not be true. We may always not be able to find. So that is, we may always not be able to find an optimal W that satisfies the above. Isn't it? So what do? We want xw is equal to y. Fine. So that implies we want xw minus y is equal to 0 or y minus xw is equal to 0. Right, we want this. Now, if this was not possible, what is the nearest thing that can be done? The nearest thing that can be done is, see, y minus xw belong to rd plus 1. Fine. Now what we can do is, we can minimize the pth norm of y minus xw. Fine. What is pth norm? Let us define pth norm. Pth norm of z belonging to rd of say r small n, say z belongs to rn, then pth norm is defined as zi mod zi power p sigma I is equal to 1 to n whole power 1 by p. What will be the tooth norm
Just
of z, which will be z 2, which is sigma I is equal to 1 to n zi squared, because you need not need mod because square actually compensates that, right? So if you want, so we usually minimize tooth norm. Fine, we usually minimize tooth norm, okay, or the second norm. So we'll pose the question as minimize r min w, that means we want to find this w such that y minus xw, the second norm, is minimized. Okay, so this is what does this encapsulate? This encapsulates the fact that I am finding a function f from this to this such that this is only a portion of this, and that portion is called the linear portion of this space of functions. Okay, no, not this. This was y.
So
in the space of functions, in the hypothesis space,
some other space.
in hypothesis space where where all these functions lie, I want to find a subregion which belong to the linear functions. Okay, linear functions. Fine. So this entire thing is just given by this. Okay, now once this is done, let us see what will happen if we are talking about the pth norm. It is y minus wx p, isn't it? If we are talking about the pth norm, what will that be in general? That will be y minus say this y minus wx xw, sorry, not wx, xw, y minus xw, say the ith element is taken, you are powering it with p, or you are taking the mod of it, you are powering it with p, and then you are taking and then you are summing it for all I is equal to 1 to n, and then taking the 1 by pth power, right? Now what is each of this? Each of this is, each ith element of this is yi minus w transpose xi, right? So I is equal to 1 to n yi minus w transpose xi, absolute value p. This was our empirical error. Okay, so the empirical error actually came out of minimizing the pth norm.
Okay.
This came out of minimizing the pth norm. Fine.
Okay.
Good. So now let us. That was just an analysis of how the Minkowski loss is defined.
Achha.
Okay. I somewhere told you about this Minkowski loss function.
Minkowski's loss.
Okay. This was for a single sample. When you sum it up and make 1 by p, that would become. So this was the motivation for single sample Minkowski loss.
Achha.
Fine. Now let us try to minimize this. Function z is equal to non y minus xw squared.
Okay.
Let's try to minimize this. Okay. Now,
Okay.
so let me give some introduction or give some overview of the matrix calculus. Okay, in this context, say we have the linear function f of x is equal to a0 x1 plus a1 x a0 x0, or let us start from 1 only, a1 x1 plus a2 x2 plus so on up to an xn. Say we have this. Suppose that I want to find df.
Okay.
That would be a1 dx1 plus a2 dx2 plus so on up to an dxn.
Yeah.
So how are you actually doing this? You are actually doing x plus dx and subtracting from f, right? That is a of x1 plus dx1, a1 of plus a2 of x2 plus dx2 plus so on up to an xn plus dxn, right? Do you see that? Fine. Minus f is a1 x1 plus a2 x2 plus so on up to an xn. This gives you this.
Right.
Do you see that? Let us try to comprehend this in vector notation. F of x is given as, say, A transpose x, where A is a1 a2 so on up to an, and x is x1 x2 so on up to xn. Let us define a vector dx is dx1 dx2 so on up to dxn. Fine. So df will now become A transpose dx. Do you see that?
Right.
From this. Fine. So we simply have, for f of x is equal to A transpose x, df is equal to A transpose dx or dx transpose A.
Yeah, because scale.
Once we have this, df is dx transpose A, we write this notation del with respect to f of x is equal to A. This notation is equivalent of this. Do you get that? Do you see this?
Wait.
This is the notation equivalent of this. Not only this, the notation this. Del f by del x bar or del x, where x is a vector, is equal to A is denotes this. Okay, this expression actually denotes this. If f belong to R and x belong to Rn. Fine.
Okay.
This is for a linear form. Now the difficulty comes in quadratic forms, which is x transpose Ax. Okay, you want to find what is df. So this is f of x is equal to this. You want to find df, or you want to simply find del x of f.
So this del x.
Yeah, we'll do that. So we know df as f plus df minus f.
Yep.
Right. So let us try to find what is f plus df, which is f plus df is simply f of x plus dx. Right. Now f of x plus ds is x plus a x plus dx.
Yes.
Now this will become x transpose Ax plus dx transpose A x plus dx plus x transpose Ax plus x transpose Ax A dx. Do you see that? plus dx transpose ax plus dx transpose a dx. Right? Fine. But then we now neglect this because we don't want dx squares. This will have dx1 square, dx2 square, and so on.
Okay.
We do usually in simple calculus, we neglect this.
Uh-huh.
So your f of x plus dx becomes x transpose ax plus x transpose a dx plus dx transpose ax.
Okay.
Fine. Let me write it again. F of x plus dx is x transpose ax plus x transpose a dx plus what is that? Dx transpose ax. Fine. Now I want to write something. Now let us write it in a different way. I will write it a transpose x transpose a transpose whole transpose dx plus ax transpose dx. Can I write?
Sure.
Fine. Now I will write this as x transpose ax plus a transpose x transpose whole transpose dx plus ax transpose dx. This is x transpose ax plus, you can replace this by f of x. Wasn't that?
Yes.
This was the f of x chosen.
Yes.
Since I can do that, I can write this as a transpose x transpose plus sorry, there is no x transpose here. This transpose has been taken out.
It goes
So this is a transpose x plus ax whole transpose dx. Right. Now this left hand side is f plus df. This is f plus a transpose x plus ax transpose dx. Now we'll cancel this f on both sides. This will now become df is equal to a transpose x plus ax whole transpose dx. Now from our other form, this becomes df is dx transpose a transpose x plus ax. Fine. So we have from our notation, this is del f of x is a transpose x plus ax. Fine. Now what does that mean? Df by dx is equal to this. This is another notation for the same. Fine.
Wait.
Where f belongs to r and x belongs to rd.
Okay.
Fine. Now in the special case of a transpose x plus ax, we can also write it as a transpose plus a times x. Now in the special case of a transpose is equal to a, that is symmetric matrices. We have del f by del x as 2ax, or equivalently del x f is equal to 2ax. Fine. So this was a prelude of matrix calculus that I intend to give you here. Now let us get back to our minimization problem. So we wanted to find the argument that minimizes, argument w that minimizes the second norm of xw the whole squared, right? The second norm squared of this. Now to do this, let us say this z is y minus xw, the second norm. This is y minus xw whole transpose into y minus xw. Can I write this way? Second norm is always written this way. Because E transpose, say E is some E1, E2, so on up to En. We know the second norm is square root of E1 square plus E2 square plus so on up to En squared. Fine. So this we already know that it is E1 square root of E1, E2, En from the dot product notation. So this is square root of E transpose E. Right. So this implies this. So we want to minimize y minus xw, the whole transpose times y minus xw. Arg min. So we took z as y minus xw whole transpose times y minus xw. Now to find the minimum, we need to differentiate with respect to w. We need to set the gradient 0. Fine. And then what is that? What do we do? It is y transpose y minus y transpose xw minus xw transpose y minus xw transpose xw plus. Fine. We need to differentiate this with respect to w. Fine. And set it equal to 0 so as to find the critical point. Maximum or minimum is later decided. Max or min is decided later. Now this is a constant. This is a constant. So this need not be worried about. The other things have to be worried about. So the other things are minus w transpose xw minus xw transpose y minus xw. Fine. Now this is your z. So z is minus c. Now let us see. These two are scalars. This is a plus. Scalars. Because both of these belong to RD. So both of these are equal because since it is scalar, I can transpose one to get the other. So we can write this as minus 2y transpose xw plus xw transpose xw. Fine. So this is actually dz by dw, right? We want to set it equal to 0. So one thing. So I have to differentiate this. I haven't yet differentiated this. So we have to differentiate this. So d by dw. Okay. Now what is this? D by dw. So there are two differentiations to be done. D by dw of xw transpose xw, and the other is d by dw of minus 2y transpose xw. Right. So let us do the first one first. That is seeming simpler. D by dw of minus 2y transpose xw. So let y transpose x be some a transpose. Okay. So this will become minus 2 d by dw times a transpose w. This will be minus 2a from the matrix calculus review that we did. So this is minus 2 times x transpose y. It's transpose, right? Since this was a transpose, this implied a is equal to x transpose y. So this is minus 2 times x transpose y. Okay. So that was the first derivative. Now the second, d by dw of xw transpose xw, which was d by dw of w transpose xw. Now let some capital Z, or no, let us say some capital R is equal to x transpose x. So that will be what? Del by del w of w transpose rw.
W transpose RW.
Okay, this has to be found. Now see, R is x transpose x. If I find R transpose, it is x transpose x whole transpose, which is x transpose times x transpose whole transpose, which is x transpose x, which is R. That is, R is symmetric, so we can simply write this as 2RW from the matrix review that we did. So let us just substitute these two here. This is RW, which R was x transpose x W, and this was minus 2 x transpose y. From the next slides. Now substituting these in this original one, we get not this. We have d by dw here to be done. Now substituting these in the original ones, we will simply get x transpose x w is equal 2 x transpose x w is equal to 2 times x transpose y. Fine. From del w of z is equal to 0. Right. Now cancelling 2 on both sides, we get x transpose x w is equal to x transpose y. Then w is given as x transpose x whole inverse x transpose y, assuming x transpose x is invertible.
First time just skipped everything and went to that.
Okay, fine. But then if you want to see it in just linear algebra way, how do we see it? If we want to see this in the linear algebra way, how do we see it? Fine.